Hello, hello, and welcome back to our regular webinar inside IBM Research. I'm Katia Moskvich, the editorial lead here at IBM Research, and today we are streaming live from IBM Research in Zurich. Thank you all for joining us, and please do subscribe to our IBM Research YouTube channel so that you don't miss any future web streams. As usual, feel free to send us your questions directly in the YouTube chat. We've got a team of great scientists here behind the scenes who will be answering your questions live. And the scientists are Gregor Seller, Basil Hess, and Kan Nguyen. And they will be happy to answer all the questions you send to us. And some of the questions we will be also answering live on the show, of course, as well. The topic today couldn't be more exciting. It's quantum safe cryptography. Now, in other words, cryptography that a quantum computer of the future won't be able to crack. Here next to me, of course, as usual, you see a model of a quantum computer. Here in the Zurich lab, we've got a real one as well. And believe it or not, but qubits here are kept at temperatures lower than in the outer space, which I think is extremely super cool, literally so, right? If you want to know more about quantum computing specifically, we will talk a little bit about quantum computers, but that's not the topic today. But we did have one of our previous webinars on exactly that, and you can go back and watch a webinar from February with Heike Ryle that talked about all the current research, recent research about quantum computing and where we are going with it. But today, don't go anywhere. Don't watch it right now. You can do it later, because right now we've got a super awesome topic as well, which is, as I said, this quantum safe cryptography. So joining me here today will be two top cryptographers of IBM Research. And the first one, his name is Vadim Lubashevsky. He is joining us first, and then we're going to talk to his colleague as well. Vadim, hello, and welcome to the show.
Thanks.
Now, I must say, I remember the day I first started researching quantum computers. I was a journalist back then, and I was working on a feature about the state of quantum computing. And I remember reading at the time during my research that at some point when these machines will be better than traditional classical computers, they will be able to break all modern cryptography. I mean, well, before we go any further, can you please clarify for us the difference? Actually, I know I'm using it a little bit interchangeably, but the difference between encryption and cryptography, and also how will quantum computers indeed be able to break modern cryptography? Vadim?
Yeah, so the difference between crypto and encryption is, I think people in the vernacular just say encryption to sort of mean that's how you transmit secret information. But that's just one small part of cryptography, because cryptography enables you to do so much more than just transmit secret information. For example, it allows you to attest that I'm the right person, I am who you want to be talking to. You can also, for example, attest to the fact that I have enough money in the bank to buy a house without actually revealing how much money I have. So cryptography is just really this. There's so much more than encryption to cryptography, and that's kind of you start with encryption, but then you really progress to really cool stuff. And how typical encryption works, I mean, that's most of it is based on math. It's not sort of explainable, but I guess the interesting thing is that there's two types of encryption. Most people break it up into two parts. There's the public key, or even cryptography, you can break it up into two parts. There's the public key cryptography and symmetric key cryptography. So symmetric key is something that people have been using for thousands of years. This is two parties come together and they know they're going to be transmitting information to each other. For example, Caesar with his generals, that's the typical how you learn about crypto, the Caesar substitution cipher, right? But then in 1970s, it was very cool. I mean, this was really something that doesn't even have, no one even thought could exist, that two people who have never met before can actually sort of transmit information secretly. And this is public key cryptography. And for that, you really need some mathematical structure to work out exactly the right way. And, and then you can have this public key cryptography. And that's actually what makes the internet possible. Without it, we would just be sort of, we'd have to first meet and then transmit secret information. But now we really can just, meet for the first time will already be talking in secret. So that's pretty amazing. And the reason, well, I think the part of your question was why don't we think it can be broken? I mean, the thing about cryptography, it's kind of a science, but it's really based on something that can there's no gravity there, right? There's no cryptography because there must be cryptography. It's just that it's based on some problems, some mathematical problems sometimes that people worked hard and said, well, this seems to be a hard problem. We tried to break it, or we tried to solve this problem, but we can't. And then cryptographers come along and say, okay, you know what, that's actually great, because now maybe we can try to build cryptography on this math problem. So the reason that it's hard is, well, mathematicians try to break these problems and they're not successful.
Cool. Well, I mean, you kind of answered part of my question, right? Like why we can break it using classical computers. So normal computers, right? It's difficult to break. I get it, but it's still possible, I suppose, right? To decode a message. But if we go to quantum computers won't be able to break it at all. Is that right? Or am I mixing two things here? If you could explain, how regular computers could break it or not, and what quantum computers could do differently.
So if the attacker does not have the secret key, then he should not be able to break it with a regular computer. So no matter how hard he tries, if we believe this mathematical problem is hard. With a quantum computer, however, there are some problems that it can break that classical computers cannot. So then the attacker doesn't even need the secret key. He can just break it because quantum computers happen to be better at attacking the specific mathematical problem than classical computers.
Right. Well, so quantum computers are, of course, very different machines. And as I mentioned previously, oh, brilliant. So now you guys can see a video of a quantum computer. So basically, they work completely differently from typical electronics simply because they rely on qubits that can be in multiple states at once. So future quantum computers would be able to go through many more computations at the same time, unlike regular computers. So why would that quality of a quantum computer enable it to break modern cryptography, Vadim?
So maybe you know more than I do. I have no idea, right? So it's kind of going back to these same math people who came along and said, you know what, these problems are actually easier in this model of computation, and so you cannot have cryptography based on that. Try something else. And so they came up with a bunch of other math problems that still seem to be hard for quantum computers. So the job of cryptographers is to kind of sift through what math problems seem to be hard, and then try to build cryptography based on them, and then try to make it efficient, try to kind of enrich it with lots of quality, lots of features. So that's kind of what we do. So we take the hard problem that the mathematicians give us, and we kind of don't even have to know what a quantum computer is, because our cryptography does not work on quantum computers. It works on regular computers, but it seems to be even hard for quantum computers to break.
Wow, okay. So when will these machines become a threat, do you think, to modern cryptography?
So that's a hard question. So I think one way, to sort of interpret that question is, when will quantum computers break encryption? So, you give it, my secret, and the quantum computer runs and says, here it is. So that may not happen for quite a while, right? So I think we're really just, IBM, Google, lots of companies, governments as well, they're trying to build quantum computers, and we think you will need about, a few million qubits, with good error correction, to actually, do something cryptographically interesting. Right now, we're at 100, something like that, and then of course there's some roadmaps that all these companies give, and they say, okay, maybe in 3 years we'll have 1,000, maybe in 10 years we'll have, we'll get to 1 million, and so I don't think we're there yet. We're not going to see it this decade. But on the other hand, if you have some secrets that you think are still valuable, 20 years from now, when people do think there's maybe a 50% chance that a quantum computer will exist that can break it, then you're a bit in trouble, right? Because because then somebody can just sort of intercept your encrypted data now. They can't do anything with it, but then they just store it until they have a quantum computer, and then they can read it, right? So if your secrets are still important to you in 20 years, then maybe, you should think of, I mean, or you already should be thinking of yourself as, kind of you've been hacked. It's just that he will only, it'll only be exploited in 20 years. So that's kind of the main motivation for why you want to switch to, start thinking about switching to some quantum safe cryptography.
Wow. Well, before we talk about quantum safe cryptography, I've just got another question here, which I'm sure lots of our viewers are interested in. Cryptocurrency, of course, cryptocurrency, Bitcoin, super hot topic right now. So do you think quantum computers will also be kind of a threat to crypto in the future?
I mean, so that's actually one of the more interesting applications of sort of attacks by quantum computers. So yes, of course, it will break all the crypto that exists, right? Because it is based on the exact same cryptography we use for communication. And actually kind of, I would say that the crypto space, the cryptocurrency space, the blockchain space is using even more kind of advanced cryptography than we're using in our daily life. So kind of replacing that stack may be quite a bit challenging, right? So definitely I would say kind of the same warning applies to cryptocurrency as sort of, what I said before. So, so if you're using cryptocurrency for something that will still be illegal in 20 years, you may want to kind of, consider, finding out what will happen, what exactly is the quantum, non-quantum safe part.
Right. Well, okay, cool. Well, now let's come actually to the actual topic of today's discussion, right? What are you guys here at IBM Research? What are you working on? Like, how can you help us solve this issue of the future? So what kind of quantum safe cryptography are we hopefully going to have in a few years' time, or maybe already have some of it now? If you could explain it to us.
Yeah, so actually, this again goes back to these math problems that people came up with. And, these problems have existed for thousands of years, let's say not thousands, but let's say hundreds of years. Some of them are kind of new that people have just started working on to say, hey, this seems to be quantum resistant. Right, so one of these is called lattice cryptography. So it's an area that comes from geometry of numbers, or from 100 years ago. And people have thought about using it even before quantum computers became a threat, but it was kind of deemed, well, why use it? We have this really great RSA and the Diffie-Hellman stuff. So, and it's kind of smaller and better. So let's keep using that. So that kind of died down until recently when said, hey, actually, let's kind of try to make it faster, try to make it, because we really need it for something. And it actually turns out with enough work, we actually put in a lot of work into this, and now it's actually faster than some of the classical stuff we're using. So, that's something we do, lattice-based cryptography. Then, I have colleagues who work on isogeny-based cryptography. So we're kind of trying to cover a lot of bases on these with these mathematical problems, trying to build cryptography on different mathematical problems, because if at some point mathematicians come along and say, actually, this is not hard anymore, then we say, okay, well, fine, we have something else. And we want to also try to make it very easy to swap between cryptography based on different problems, because before, in the 70s, 80s, we really only had one type of public key cryptography. There wasn't a lot there. But now we have a lot, and so now it kind of makes sense. Hey, maybe we want to try to switch it easily, because maybe one will be faster, one will be more secure, things like that. So just so we don't have to go through this, oh no, all cryptography is broken. What do we do? You say it's okay, we just switch. So that should be easy.
Cool. Wow. Yeah, definitely really, 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 really interesting. Let me now invite your colleague, Mike, to join us here. So Mike is responsible for the deployment of quantum safe cryptography here at IBM. So Mike, a question for you here. If quantum computers of the near future will indeed be able to break all modern encryption, what can we do today? How can we get ready? What's your advice? What's your take?
So hi, Katya. Thanks for the question. Well, I think we have to look back in time a little bit and understand that we've had to migrate crypto in the past because things have been broken. But actually, it's proven very, very difficult. We as an industry haven't really done a very good job in migrating crypto, and we should have. It takes, on average, for large organizations, 5 to 10 years to actually find all of the cryptography that they have, figure out how it's being used, and then actually migrate it to new schemes. So many bad examples from the past, which is why we're really keen to actually get things right this time. And so IBM, based on our own internal experience over the last few years, we've been looking at these new schemes. We've been looking at what it takes to migrate our platforms that use these schemes. And we've developed a fairly comprehensive roadmap on what you need to do as an organization. And I think there are really three key parts. The one is really to understand the risk in your organization. Now some organizations, they're not going to have data or systems which are particularly the data that they're protecting is not particularly sensitive in the next years. So maybe not such a problem. But there are many other organizations where that data will remain very sensitive for a long time. So it's really understand the sensitivity of the data that you have, understanding where the crypto is that you're actually protecting it with, and really understanding, okay, when it makes sense to move or to migrate that application or system to quantum safe. Now, there are things like legacy. I'm going to talk about legacy a little bit because migrating legacy things is difficult, takes time, complex. It's actually much better, especially now, to prevent new legacy being created. What do I mean by that? Is really getting an awareness of, for any application that you're building or any legacy system that you're currently migrating to the cloud, is use those projects to actually start to prepare for being able to transition cryptography. The last thing you really want to do is, have a big cloud migration project or a big legacy system project, and then have to upgrade all of the cryptography in the coming years. And I think that's particularly relevant to the question you asked around crypto tokens, cryptocurrencies. We see that these things will be around. We all assume they're going to be around. We don't know what the value will be in 10 years' time, but they'll be around in 10 years' time. So really, rather than sort of, if you're planning to roll out new systems around tokens or crypto, really take a good look at how you can be prepared to migrate cryptography, really with the emphasis on preventing new legacy being created now that's going to come and bite you in the future.
Super cool. Let me just address our audience here for a second. So guys, the viewers, do send us your questions on cryptography, possibly. I know there are some questions on quantum computing right now, but it would be great if for our experts you actually ask cryptography related questions more, or the future and research they're working on now. So please do send us your questions. Now, as you were saying that, Mike, actually it reminded me for some reason, I don't know why, but I just remembered this knapsack problem that is sometimes used to illustrate quantum safe cryptography. And Vadim, I think you mentioned that to me previously. Can you maybe explain that a little bit more? And I believe we even have a video to show. If you could talk about that a little bit.
Yeah, sure. So this is one of these. So the interesting thing is this is one of these problems that illustrates lattice cryptography. So it's similar to lattice cryptography. And kind of the interesting part is that when you look at it, for example, there's classical cryptography is based on factoring, right? So you're given a large number and try to find two factors of it that multiply to it, whose product is that number, right? And people say, okay, that one is hard, we think, for classical computers, but quantum computers can solve it. But then you see this other problem, this knapsack problem. You'll see it, and it doesn't look that difficult. It's like, yeah, okay, sort of. It's not some weird problem that you cannot, quantum computers can't solve because no one can understand it. It's a very simple to state problem, and yet we somehow believe that quantum computers cannot solve it, right? So kind of an interesting question is, why do we believe this? How come? Or maybe they can solve it, we just haven't found the algorithm for it. Right, so we'll watch this video maybe twice because it goes kind of fast, right? So let's give a toy example, right? So let's say there's, you generate 6 numbers between 1 and 50, and everyone gets these numbers, right? So they're on the screen now. And then, I secretly pick 3 of these numbers and add them together. And I tell you the answer is 96. And now, well, that one's pretty fast. Now it was your job to find which 3 numbers I added to make 96, right? So with small numbers, the problem is solvable. But once you have 1,000 numbers, with thousands of digits, well, now this problem becomes really difficult. I don't know. I don't know, Katya, was that fast? Or maybe we can watch it again with. Can ask Marcel to one more
Good
time.
idea.
Yeah. Okay. So yeah. Okay. So now we kind of know what to expect, right? So now we're going to generate 6 numbers between 1 and 50, right? It's 6 random numbers. I mean, okay. So here they are again. And now I'm going to pick 3 of them. So I chose 3 of them. And then I summed them up, and the answer is 96. And now, can you find 3 of these numbers that sum to 96? And here they are. That would be the answer. So basically, that's the hard problem. And why is it hard, right? It seems kind of even simpler to explain than factoring. There's no number theory necessary, and yet this seems to be a hard problem for quantum computer to solve. And surprisingly, we can base a lot of cryptography based on problems that are very similar to this.
Thank you, Vadim. That was actually quite a great example illustrating quantum safe. Now, I'm just wondering, have you guys already tested quantum safe encryption in the real world? I guess question more for you, Mike, right now.
Yeah, absolutely, we have. It's a really important aspect. I mean, it's to figure out what the implications are of this new cryptography, because it's different. It might be simpler to explain in a video like we've just seen, but it has different characteristics. It's a bit faster, but sometimes the keys may be a little bit longer and stuff like this. And so it was really important to understand what it means for our systems to use this new crypto. So, for example, our encrypted tape drive sounds like a funny example. But our tape drives are designed to protect data for a 30-year lifetime. So that's well into the era of large quantum machines, potentially 30 years. We have provided this actually to our clients on our mainframe platforms. So mainframe platforms, some of the applications which run on mainframe platforms, they last decades. So we really have seen that, while there may be some debate about when actually these machines will actually be able to break something, a lot of the technology that we deliver actually has much longer time frames, really multiple decades. So in answer to the question, yes, it's been a very important aspect of understanding the characteristics of the algorithms, understanding what we need to do to migrate, and then actually capturing that information and making that available to our clients.
Okay, yeah, that makes sense. And actually, there's a question from the audience for you, Mike. As you were saying that, it just arrived. Is quantum safe cryptography going to be very important to IBM System Z Linux One customers in the near future? What's your answer to that?
Yeah, absolutely it is. So I can't go into too many details on the roadmap, but I can tell you that the first quantum safe algorithms have already been released and are available on that platform for our clients. And that's part of a strategy to make that entire platform completely quantum safe. We're the first large quantum safe platform.
Okay, cool. Here's a question for Vadim, also from the audience. As we speak now, questions are coming in, which is exciting. Has the standard for post-quantum cryptography been decided yet? And what's going to be the cryptographic standard of the future? That's a good one.
Yeah, so right. That's a good question. And actually, I mean, it's quite pertinent, because right now there is a standardization process happening run by NIST, the American standardization body, that has actually standardized before. They unstandardized AES and SHA-3, which are now one of the more some of the most common used block ciphers and hash functions. And so now they're running sort of edged on by the need to actually have quantum safe crypto. They started something in 2017. And there's been a lot of activity in that area, and this is kind of how. And this is very important, not just to select some algorithm, but also to gain confidence in them, right? Because you want people from all sort of walks of mathematics to look at your crypto algorithm to see, well, is it really hard or not, right? So this is it's been a very good process. It's been around going for 3-4 years, and I think NIST has promised something that will be standardized maybe next year. Something will be chosen, and then the drafts have to be written, and maybe 2 years after that, we actually will have standards. But all of this is so IBM, we've been very actively involved. So now we're at the finalist stage. So we have I don't know, three out of 6 or something like that is we have in there, so you can actually use these right now in some sense, right? So you don't you can actually experiment with them. They're all you just kind of Google NIST standardization, NIST post-quantum standardization, and you will get this list of the algorithms that are currently the finalists, and they're all open source. You can just use them, see if you like them, whatever. So it's kind of really we do want the community, not just the people who invent these algorithms, but people who use them to actually be active and say, we like this part, we don't like this part. So this is kind of very important, and so once that's over, we will have good standards, we hope.
I'd like to add something there if I could, and that is that you shouldn't wait until the standards are ready, because 80% of actually moving to these new standards is the preparation to do so. And that's all stuff that can be, let's say, that can be sorted out now, can be addressed now in preparation for when these new standards arrive.
Yeah, that's a very good point, Mike. Thank you. And going back to quantum computers for a second, again, I know, Vadim, you mentioned earlier that you don't know much about quantum computing as such yourself, because you're a cryptographer, obviously not a quantum physicist. But still, I'm just wondering, to do this kind of work that you guys are doing, like, don't you need quantum computers at all, or do you need to simulate them maybe in any way, or like what's the process, if you put it like really simply?
So for what I do, you don't even need a regular computer, and it's all really you're given like I said, you're given some mathematical problem that people think is hard, and then you kind of try to design cryptography based on it. And even the mathematicians who decide whether this problem is hard or not, and that decide to try to work on it, they also kind of don't need computers, right? Because even quantum computers, because they know this is the model how quantum computers work, and they say, okay, in this model, what can we do, right? So there's no one has decided that classical cryptography is easy because they actually broke it on a quantum computer. No, they just have a pencil and paper algorithm. But of course, I mean, yes, you do need a quantum computer if you're going to do some things which are maybe unpredictable. Yes, of course, you need. But that's not what we do. Everything we do is completely, mathematical.
Right. Well, so what about because there's also quantum cryptography, right? So you guys are doing quantum safe cryptography. So what's the difference between, because I'm sure lots of our viewers have heard of quantum cryptography as well. Is that a thing, or is that completely different? What is that really?
So it's very different, right? So quantum cryptography actually needs some either a quantum computer, or like a quantum key distribution. You don't need a quantum computer, but you do utilize some quantum properties of nature, right? So for that, yes, their problems do involve building things, because they're kind of trying to solve something else. I mean, they're trying to solve how long can the signal go for, how far can we transmit this? So that's really a physics question here. But for us, we design schemes that can be run on classical computers. So to test them to see if they're fast or not, we just run them on a classical computer or a phone or a smart card. People have been doing that. So yes, but the quantum computer, you need a quantum cryptography. You need a quantum computer, and we don't do that. We don't here at all.
Okay, thank you. Actually, interestingly enough, now we just watched twice the knapsack problem video, which was super cool. And somebody here is asking a question, a follow-up question on the knapsack problem. Is there a way to be sure that for any sum, the 3 numbers are unique? That's a good one.
That is a good question. So that really depends on how many numbers you have and how many digits there are. So so if there's a lot of numbers that have very few digits, then it's not unique. It's almost certainly not unique. On the other hand, if you have not too many numbers, but they have lots of digits, then with very high probability, it will be unique, right? And actually, this question that you raise, it's like depending on whether we have a few numbers with lots of digits, but of course, a few, I don't mean 3. I mean, 100 numbers with 10,000 digits, or 1,000 numbers with 500 digits, right? So depending on which of these scenarios you're in, you can have different types of cryptography. So some type of cryptography is based on this type of problem, this type of scenario, and another one can be based on different type scenario. So, but that's kind of not super important if unique or not. But yeah, that's definitely a very good question, and perceptive, sort of in terms of what is important in that problem.
Great, thank you, Vadim. And here's a question for Mike from the audience. This is surely going to be a rapidly changing environment just due to the quantum nature. So what's the comfort level to the adoption with a single standard approach? So
that is a good question. So, and interestingly, NIST is aware of that challenge, and so they will actually standardize a portfolio of algorithms based on different mathematical properties, just to have the Swiss Army knife of alternatives should one particular mathematical problem prove not so difficult on a quantum computer. So what does that mean, actually? So what does it mean generally if you're entering a period of uncertainty where you can't really predict or forecast what's going to happen? Then all you can do is have the ability to change quickly. And this is what we call the topic of cryptographic agility. So essentially write our systems and prepare our systems that we can very quickly change to something else if it looks like what we're currently using has been broken.
Right. Okay. Thank you very much for that, Mike. I remember actually reading, and I've also written something in the past on this other type of encryption that is also, I believe, considered quantum safe, fully homomorphic encryption. I'm not sure if anybody in the audience has heard of that, maybe read some articles on that. Is that fairly similar to what you guys are talking about and what you're working on, or is that something completely different? It's also quantum safe?
Well, it's definitely very related, right? And so this fully homomorphic encryption is it's actually quite amazing, right? So remember, I think in the beginning I said that there's public key encryption, where, for example, I see you and Mike on the screen right now, and we haven't prepared anything, but I can actually start communicating with Mike. We can establish something. You hear everything we say, and yet we will be able to exchange secrets, without you being able to sort of know what we're saying, even though we haven't established anything prior to this conversation. So that's public key encryption, and pretty amazing, And fully homomorphic encryption, I would say, is even more sort of amazing in the sense that sort of more unlikely to exist. And people have asked this question: can you do it? For 30 years, and it's only been kind of resolved not too long ago, a decade ago, by Craig Gentry, who was a scientist at IBM. So fully homomorphic encryption is the following, right? So for example, let's say I want you, because you have a quantum computer behind you, so you're obviously much more powerful. You have more than my cell phone here. So let's say I have some problem that I would like to, I need some computation done, right? But my phone cannot do it, but your quantum computer or whatever you have back there can. Right. So, but of course, I don't want to tell you the inputs to my that's my stuff, right? So amazingly, what I can do is I can encrypt my inputs and just send you the encrypted data, and then you will run some algorithm. This is the evaluation algorithm, part of fully homomorphic encryption, that's going to run on this encrypted data, right? So any function you want, any function I want, you can run it, and you have no idea what's going on. You're just computing. You have no idea what I said, and at the end you get an answer, which is encrypted, and you have no idea what's there. You send it to me, I decrypt it, and I get my answer, right? So that's fully homomorphic encryption. So it allows you to compute on encrypted data, right? So that's what it is, and so it just so happens, no one asked, can you make it quantum safe? It just so happens that the way that it was built, and the only way that we know how to build it up to now, is based on lattice cryptography, which is this knapsack problem type thing that was related, right? So it's quite powerful. This lattice cryptography can you can build a lot of stuff from it. So that's the relationship. So I personally don't work exactly on it. We kind of know what it is. We use it. We read papers about it. So IBM, other people at IBM work much more extensively on it. But so that's the relation between. And sort of the nice feature is that it's quantum safe. So that's kind of a big bonus, I guess, at this point.
Right. And so I suppose it's also when you were describing it, so basically with this type of encryption, both the kind of the data and the algorithms remain encrypted even during data processing, right? So it's quite different from, for example, when on WhatsApp they say, end-to-end encryption, or even, Telegram, for instance, or Signal. Everybody is now using Signal messaging service. So how different is that from that type of encryption? How much safer is that?
I think I take this one. Yeah. So I mean, it's along those lines. I mean, if you look, the problems that we have today is that we encrypt data when it's stored, it's safe, it's fine. We encrypt it when we move data, safe, it's fine, assuming it's quantum safe. But when we go to use the data, we have to decrypt it, and that's when all sorts of things start going wrong. The applications leak it, that we don't do. We have to manage encryption, decryption. So the ability to encrypt data once and then keep using it in a confidential way is really important, because it's going to save a lot of, I would say, security holes. The other thing which is really important, and you alluded to it, is that the processing is confidential. So maybe not many people know this, but AI is really important in today. It's AI typically works by you train an algorithm over lots of training data, and then you use it to do something like decision making, inferring, whatever. Now, it just so happens that the processing, the AI model that's created, is like a compressed version of the data it was trained on. So if that leaks, or if somebody gets the model, the processing that you use on the data, it can actually leak a lot of sensitive data. So it's really one of the very interesting ways to protect, for example, the use of AI and the sensitivity that is built into AI models. So that really kind of is I think a very good example of the sort of why the processing part is as important as the data part.
Mm-hmm, mm-hmm. Okay, so for example, I'm just thinking out loud here. If it would be possible then, if we're talking about homomorphic encryption, to use AI to maybe match a patient for a clinical trial based on their genome sequence, and the genome sequence would be homomorphically encrypted in the cloud, right? So the system would then output an encrypted match effectively without exposing any sensitive data or the result to the person who is actually doing all this processing. Is that right? Would that be a good use of homomorphic encryption, like confidential computing in a way?
No, I think it's a very good use case. So one of the problems that people have is they're reluctant to put data even encrypted in the cloud, because to use it you have to decrypt it, and things might go wrong. So the pure fact that you can put encrypted data in the cloud and never need to decrypt it is offers a very kind of like high assurance. So that's, I think, it's a very, very good use case. And now the other thing is that data that you put in the cloud, or that you bring together or put somewhere else, it is not by design, but by attribute quantum safe. So actually using that sort of encryption actually future proofs the security of the data that you're putting somebody else. It doesn't matter so much. If somebody loses the data on that cloud, because it's encrypted in a way which is really future-proof. So it's a very good use case.
Cool, thank you. Here's a question from the audience, and probably for you, Vadim, or I don't know, or maybe for you, Mike. You guys decide. Do you believe that the use of quantum safe cryptography will continue to be high if quantum cryptography becomes more widespread? So back to the debate between, well, not to the debate, but to distinction between quantum safe and quantum cryptography.
Yeah, so I mean, yes, of course, right? For example, even if quantum computers are prevalent, right? So let's say that model behind you actually becomes real, and we actually do have quantum cryptography, which is unclear what advantages it has over quantum safe. But let's say we're not going to have quantum computers in our pockets, right? We're not going to have quantum computers on smart cards. I mean, it's going to be in laboratories. It's going to be right. No matter how advanced we get, I mean, probably, right? We're not going to have. So for those use cases, you will absolutely need regular, classical regular cryptography that can run on classical computers. So it's definitely not not something that will die out.
Maybe just also a point from my side that things like quantum key distribution, quantum cryptography, they address a small part of the sort of crypto that we need. So this comes back to the original question, the difference between crypto and encryption. So there are a whole set of things that we need to do, like digital signatures, things like this, that those techniques are not able to deliver. So what we need, actually more importantly, is something that we can use today to replace all of the crypto that we need to replace today. And then maybe for those use cases where it does make sense for quantum key distribution, quantum cryptography, then it's more of a delta to all of the other use cases that we really need to get right with quantum safe cryptography.
Right. Thank you for that, guys. I should mention something. So Vadim, not to confuse our viewers here, you did say once this model becomes a real computer, right? Well, just to correct you slightly there, because we do have them, of course, even here in Zurich, right? There are, so that our viewers are absolutely clear, we do have quantum computers and they are working. We're doing research on them. It's just that we haven't yet achieved, quantum advantage, and they're not yet better than traditional computers. So for that, you can watch our previous webinar where Heike Ryle explains it in beautiful detail. But you're right that it's not. We are not there yet to use them for them to be better than classical machines. But I'm pretty confident we will get there in the future. So now back to what you were saying. On quantum safe, right? It does sound amazing, obviously, and it's super cool research, but how confident, and I'm sure some of our viewers probably asking themselves this question, how confident are you that these methods really, really won't be broken by a quantum computer of the future?
So I think it's the third time you asked me this question. Yeah, my answer kind of doesn't change. We have no idea, right? Let's say Personally, I'm not even confident that classical cryptography can't be broken by classical computers, right? Who is to say that factoring is hard? So I think I remember, maybe 20 years ago, they did some survey when RSA cryptography was kind of not as old as it is today. They did just surveys of mathematicians who attended these theoretical cryptography conferences or theoretical computer science conferences. Do you think factoring will be broken in the next 30 years? And I think half of them said yes, it will be. And they weren't thinking about quantum computers; they were thinking about classical computers, right? So, this is one of these things you have no idea, right? So the more people you have looking at this mathematical problem, the more confidence we get that, hey, this actually is possibly hard, right? So, now, like I said before, now with the standardization process that NIST is doing, a lot more people are looking at these problems, even though these problems have been around for 30 years. But the question is, was there a big, amount of people looking at them, trying actively to break them? And now I guess there are, right? And so we as they're put into use more and more, we will get if they're not broken, we will be more and more confident that they really are okay. But in terms of probabilities or how confident, it's impossible to quantify, right? I guess people can start some sort of wager markets, right? And then you can see what they're betting on, right? But other than that,
yeah,
no.
That's for sure. It's pretty tricky to quantify. That's true. But people are still wondering because it's technology of the future after all, and it's all super cool. Question here from the audience on homomorphic encryption. Going back to homomorphic encryption, what kind of transformations does this encryption preserve? Does it make sense to add 2 pieces of fully homomorphic encrypted data, for example? Who wants to take it? Mike, maybe, or Vadim?
So okay, I can try to take. So I'm not quite sure I understand the question. What kind of transformations it preserves? What it does is it outputs. Somebody who gets the encrypted data can output the encrypted version of any function evaluated on this data, right? So that's kind of that's what it does. So I'm not quite sure what is meant by transformation, what kind of transformation it preserves.
I think there may be there's some misunderstanding that FHE is FHE. There are very many different FHE schemes which are more or less efficient at doing different things. So essentially, if you can add and multiply homomorphically, then in theory you can create almost most computer problems out of those two capabilities. It's just that some of them are more or less efficient. So it's really, I think, less about the transforms, more about the efficiency of the actual processing that you want to do using one of the many different schemes that are available.
Right. Okay. Well, maybe the viewer who asked that question could clarify it for us. But for now, yes, Mike, as you were speaking, actually, if we go back to use cases, we talked about genomics a little bit. Maybe you can give us examples of other use cases, not specifically for homomorphic as such, but just for quantum safe cryptography. Where could it be used? For which industries? For which clients? For which fields?
I'll start with the easy ones. If you're building a satellite now and shooting it up into space for a 30-year thing, might be good to think about putting quantum safe crypto in that today. If you are building an aeroplane or building a car that's going to be up in the air or on the road for a couple of decades, you should already be really thinking about at least how you can update those things as we enter the quantum era. Again, it comes more to the preparation because updatable cryptography, so moving from something which is not quantum safe to something which is quantum safe, that is a function that very few people think about. And I think there are many, many industries. We see it everywhere. Bitcoin, I mean, maybe they should have thought about that 10 years ago because it's going to be very difficult to migrate Bitcoin to be fully quantum safe. The same with any crypto token that's going out there now, except those which are already quantum safe. So I think anywhere where either the data needs to be protected for a long time, or they are systems which hang around a long time, which is an incredible, it's a lot of industries and a lot of platforms and a lot of data, then they are all, let's say, important candidates. And it's not about, let's say, at some point, well, maybe we should think about it or not. In many industries, this will be regulated and legislated. So it's something that many organizations will have to do at some point.
Right. Okay. Yeah.
So maybe if I can add a little to what Mike said. So like the one use case that I find most fascinating, not because it's the most important one, is really cryptocurrency, right? Because there you kind of have the perfect storm of things that is a problem, between switching from one cryptography to another. One is that, remember in the beginning I said that, even though we don't have quantum computers now, somebody could be, intercepting your data and then getting ready for, waiting for a quantum computer to appear. In cryptocurrency, the whole blockchain thing, all your data is by design sort of already intercepted, it's stored, right? So that's kind of like, nobody has to intercept your data. It's there, right? Secondly, another feature that many blockchains have, and I guess a lot of cryptocurrency, is the decentralization, right? So it's not that, right now, if IBM wants to migrate to quantum safe crypto, they, get some IBM software engineers to migrate to quantum safe crypto. But, the decentralization aspect of it is very interesting because now you actually have to have the users themselves do something. Right, and just to see, I'm just very curious to see if this, thing, actually happens, how it will happen. It's, I find that, I want to sort of be around to see that, just as from a fascination, perspective.
Absolutely, yeah, me too. Here's a question from the audience here, a little bit too technical for me to understand, but I'm sure you guys will understand. What do you think about the next step for the quantum safe, lightweight, symmetric cryptography? What does that even mean?
So, right. So like I said, there's two types of cryptography. There's public key and symmetric key. And, for symmetric key cryptography, I mean, that's the one that's existed for thousands of years. Two people come together, they exchange some secret. No one knows the secret except them. And then using the secret key, they can kind of communicate with each other. And so, classic example of symmetric key encryption is AES. right? So this is something that's been standardized 20 years ago, and it's been used. And that is quantum safe. So, symmetric key cryptography does not seem to be impacted more than just a little bit by quantum computers. So no one is, for example, the NIST, the standardization body, is not worried about AES, so there's no competition to kind of phase it out and put something quantum safe in. So all the symmetric key stuff you're using is perfectly safe.
Super cool. I've got another very technical question here that we will probably finish with, unless there will be other questions from the audience in the next 5 minutes or so. Can we say that in the end, it all boils down to the problem P equals NP, in the sense that for some problems, it has already been shown that even with a quantum computer, it is not possible to reach an exponential speed up?
Okay, so in order to prove cryptography is secure, so this is the question you keep asking, are you sure? Are you sure? So if you can do that, right, then you actually did prove that you separated P versus NP. Of course, P versus NP is the central question in theoretical computer science, right? It's the separate, things that can be solved in polynomial time versus things by regular computer versus things that can be solved non-deterministic polynomial time. So basically, this is the question of, finding the answer and verifying the answer. Is one easier than the other, right? So of course, everyone believes that verifying the answer is much easier than finding it, right? So this is the kind of what the question is asking. So if we can actually prove that P is not equal to NP, then we have a chance to say, hey, this crypto is actually secure. And I think the question also said, hey, didn't we prove that quantum computers can't solve some problems? And so there was no proof that they can't solve problems in NP, but if they can solve NP-complete problems, then some weird things happen in that the theoretical computer scientists believe should not happen. So we don't think that quantum computers can help with NP-hard problems, but cryptography is not based on NP-hard problems. So regardless of what happens there, even if they can't solve NP-hard problems, they could still break cryptography.
Right. Great. Thank you. And I guess just the last question here for Mike. What is the computational cost of fully homomorphic encryption? And I suppose probably also other types of quantum safe cryptography. Aren't they too heavy duty for practical applications, for widespread, I guess, practical applications?
Yeah, I think it's a good question. It's a question we get very often, and it's all a big depends. I mean, a few years ago, it was really more theoretical and took many more cycles than were practically possible. But it really depends on the scheme that you use, the strength of the security, and the problem you're solving. We have, for example, use cases. So some use cases, it's really only a factor of 50 difference in terms of the overhead. Some use cases, it's several orders of magnitude more. So it really all depends on what you're using it for, how you're using it, and how much data you're trying to push through it, that sort of thing. So there's not one answer. It really it depends.
So just to follow up to that, so is it possible then in the future to use quantum safe cryptography on IoT, mobile devices, or not?
Yeah, so that was more an FAQ response.
Go ahead, Mike.
Go ahead, Vadim.
No, I was just going to say the future is now. I mean, you can actually, like I said, all these things in this standardization process are available, and people have implemented them on very low-power devices, and it seems to be okay. So there's no problem there. But go ahead, Mike, you want to add?
No, I was going to provide the same response. So many of the quantum safe things are actually very somewhat simpler to actually implement. And as Vadim mentioned earlier, some of them are actually more performant than some of the crypto that we use today. So no reason not to be using this for IoT devices.
Well, that's super encouraging. So in the future, I may have a smartphone with quantum safe cryptography and a quantum computer won't be able to break it, right?
Sure.
That's That's super
If
cool.
I could add with maybe on a down note, I mean, you shouldn't be finding this so exciting. This is kind of, it exists. It has existed for a while, right? So I mean, it's kind of, the cryptography is just supposed to be, sort of behind the scenes, just keep it, and it's, it's there. It's just based on math, just like the other cryptography we used before, right? So it's exactly the same thing, just based on different math problems. So there's no reason that shouldn't exist.
Great. Well, that's even better, Vadim. So the future, what you're saying, the future is now. This is amazing. And I'm sure everybody is super excited by it. Well, thank you so much, guys. Thank you, Mike. Thank you, Vadim. And thank you to the scientists who have been answering, I'm sure, lots of questions in the chat as well. And of course, thank you to everybody who joined us today for this webinar. Just to repeat, please don't forget to subscribe to the channel so that you don't miss any future webinars. And you can always go back and watch the previous ones because they're going to be here on IBM Research YouTube channel. It was great having you all. You can always reach out to me personally on Twitter at SciTechCat with any questions or comments or ideas you might have. And I hope to see you all at the next webinar next month. Thank you very much and goodbye.
Bye.